Okay. Okay, so let's get started. Um, it would be nice if some of you, or all of you, can activate your video. Please do that. Thank you. Okay, so we are in this chapter that we just started last Wednesday, which is entitled Elementary Graph Algorithms. And as I pointed out when we first did chapter 23, that it was in a way a bit out of order because this is the earlier chapter which gives the introduction into graph algorithms. So in particular, we already reviewed this slide. I'll go over it again simply because it is so elementary, and this is one of the things that you must have in the back of your mind whenever you talk about graph algorithms, because the basic trust of almost everything that we do in this course in the algorithms chapter that you get a certain input, and then you're supposed to produce an output. And we reason about the correctness and complexity. But what is often a bit easier to forget is that the form of the input is critical, because it will define what you start with. And unless you fully specify it, it means that what you have provided or what you are considering is ill-defined. So it's very important to be very clear when we talk about a problem that takes a certain input and produces an output, what is the form of the input and what is the form of the output. And as we are going to see, whenever we talk about graphs, we have two standard representation of inputs. And the complexity will be different of many of the algorithms we discuss based on the input representation. So for that reason, it is absolutely critical to be aware of it and to fully specify it, because otherwise what you say may be, as I said, unclear. So we are talking about two types of input representations. I'll go quickly over this slide just to remind you. One, in a vertex you have in a graph you have vertices and edges, and this is an example of an undirected graph which has 5 vertices numbered 1 up to 5, and it has a total of how many? I think 7 edges. 1, 2, 3, 4, 5, 6, 7. Yeah, 7 edges. And so we have here a matrix of 5 by 5, which if we have a 0 in the entry 1, 3 right here, it means that there is no direct edge from 1 to 3, no direct edge. But if there is an edge, say from 2 to 5, then if we go to location 2, 5 here, we will see a 1, not a 0, because there is an edge. And because the graph is undirected, we'll have also another 1 in the location 5, 2, because the graph is the matrix is symmetric around the diagonal. Because that's the whole definition of undirected graphs, that if there is an edge from 2 to 5, there is an edge from 5 to 2. So this matrix has it in its the redundancy that if you take the diagonal as the symmetry axis, what is on the upper side is a mirror picture of what is on the lower side. So it's going to be fully symmetric, meaning Aij equals Abi. What are the features of this matrix multiplication for matrix representation? I'm sorry, adjacency matrix representation for input when it is used as input for graphs, that its space is n square, regardless of the number of edges, but the time to process a query of the form, do I have an edge from I to j, is order of 1, because we simply check whether it's a 0 or 1. The adjacency list representation has potentially lower space, especially if the graph is sparse, meaning where the number of edges m is significantly lower than n squared, or in other words, where most of the entries are zeros. And here we have an array of size n for the vertices, and out of each entry, you have outgoing here a linked list with all the edges. So every edge will appear here twice because, for example, the edge 2 to 5 will appear here somewhere in the linked list of 2. This is the 5. And it will also appear here in the linked list for 5. That's this 2. So the upside or the big advantage, the big pro of adjacency list is that the space is lower. The downside is that no matter what you do, even if you sort the edges, the vertices on the other side, so to speak, you cannot get it down to constant time for the query is Ij in E. And as you notice here, the standard representation does not assume that the edges are sorted or the nodes on the other side. Okay, so this is so far the standard representation of graphs as we are going to assume throughout this chapter. And in fact, we assumed it already in the chapter that we reviewed. We just sort of swept it a bit under the rug, the chapter on minimum spanning tree. Okay, when it comes to directed graphs, here the graph is not symmetric because the directed graph means that there is an edge, for example, from 4 to 2, but the fact that you have an edge from 4 to 2 does not mean that you have an edge from 2 to 4. That's the whole idea of a directed. So in a directed graph, every edge is a directed pair where the head and tail are different. And here, every edge will appear only once in the adjacency list, and the matrix here will not be symmetric. So I hope that these 2 points are quite straightforward, and I'm going to proceed now to describing some algorithms. So the first algorithm that we are going to consider is BFS, which stands for breadth first search. Okay. So what is the basic idea behind a breadth first search? So I'm going to first give you a very high-level description, and then I'm going to jump to proceed to the description as appears in the slide and in the book, and I will actually try to make you alert to a certain indoctrination that is a bit obsolete, which is reflected in the way that the book, and I'm in fact going to present breadth first search to you in the slides. So what is really breadth first search? Breadth first search is the following concept. Here you have a graph. and it's an undirected graph. And I would like to do to compute for a certain vertex out of it. It comes as part of the input. Vertex S, I would like to compute the shortest distance from S to every vertex in the graph, counting edges. Meaning, what it will mean is the following, that if this is S, then R and W are of distance 1 from S, V is of distance 2, because you need 2 edges to get from S to V. X and T are distance 3, and U and Y are of distance 4. Is the definition of the problem clear? What I would like is you give me a graph, an undirected graph, and I would like to compute D of V, which is distance of V, from the source node S. So I'm getting as my input, I'm getting a graph, vertices and edges, and a source node. And now the problem is output D of V, meaning for every V in the graph, meaning find the distance, which is the shortest path counting edges, the length of the shortest path counting edges from S to every node. And of course, if there is no path, I want you to give me an infinity or something that that will tell me that you didn't find anything. So I hope that the problem definition is clear. And now that the problem definition is clear, let us ask how we would like to think about a breadth first search and solving the problem without bothering in a way that will feel like an algorithm, but will not look too much like a low-level program. So the answer to that is really what breadth first search is all about. So the idea is just you can think about sort of sending a wave from S through the graph, and the wave goes in all directions. So if I send a wave, suppose they are connected, I don't know, by pipes, and I send a wave of water, and suppose the water advances synchronously. Which nodes will I reach first from S? I will clearly reach W and R first, right? Because I send water in all pipes, and they will be hit first. Okay, so imagine the following algorithm where I mark simultaneously, concurrently, R and W as 1 away. Okay, now, in this sort of wave propagation algorithm, I now let the wave proceed to the next synchronous step. To the next, so imagine that it walks in pulses. Pulse 1, it reaches 1 away, which is R and W. Then I look where it goes when I send it further. When I send it further, it will reach 2 away. And who will I reach? I will reach V, T, and X, right? And then I will send it 3 away, and I will reach U and Y, right? So just imagine that I have a pulse here where each time my wave goes 1 way further. And the slightly confusing thing here is that when it goes from T to U, it will also go to X, which is already being visited by a prior wave. So just ignore it. Let's assume that we only look at newly discovered nodes. So this is really the heart of breadth first search. And I hope that you see that there is a certain element of parallelism in it, because the wave, of course, is limited by the structure of the graph, but I'm not conditioning that I will reach R before W or W before R. And when I go further, I'm not conditioning to reach V before T or X. Any order is fine. Actually, what I described reaches all of them simultaneously, right? So the point here is that this is really the idea of breadth-first search, and it really is captured very nicely by the word breadth-first search. You go in all directions, you go broad, rather than go deep, which means you pick one direction and you proceed, which we are going to study later. Here you go broad. You go in all directions without discrimination of any direction. You just advance to the next. So it's like a wave that you keep pushing. Okay, so if this is the image you have, I think that that's really you already understood the spirit of what breadth-first search is all about. However, what you're going to see next is how, in a way, messed up the description of breadth-first search that I'm going to give you by following on the standard representation in the textbook. So when I'm criticizing it as a bit messed up, it's definitely not my contribution. I'm just teaching you the way that it is being taught everywhere. So what is really the issue that that guides the way we are going to actually study that? The point here is that your standard computer, let me put it this way, the standard serial interface of computers does not allow me to tell you go in all directions at the same time. You are allowed as a programmer in the main model that we study in this class, not in the Pira model that I mentioned in the background that sometimes I remind you of, not in the parallel model that is the subject of my 651 course, which will probably be taught only in spring of 2022 as it looks now. But in the current course, everything must be serialized. And so what you will see in the way that I'm going to describe it to you is that the serialization actually in the mind of somebody who just is exposed to breadth-first search the first time, as I'm going to show you now, without my introduction on how to do it in parallel in a wave type form, in their mind, they are being taught to actually think about the serialization as part of the definition of breadth-first search. Okay, so when I told you go in all directions at the same time, this was in fact illegal for this class. Because in this class, what I'm allowed to do in the main programming model or algorithmic model that we are operating within is only to tell you what is the single operation you have to do next. So in order to do that, what we are doing, and maybe by now I think we can go back to the code and give a short overview of that. And then I'll come back to the example. I hope that it will not be too overwhelming to look at the code. It's not a very, very difficult code. So basically, the idea will be to have an initialization phase where for all the vertices, with the exception of S, which is the start node, which, as I said, comes with the input, we initialize their color as white, which means that they have not yet been visited. And the distance to them initially is infinity, because I don't know if I'll ever be able, to reach them. And even if I will, at the present time, I don't know by how far. And as far as I'm concerned, it's a very high number. It's infinite. And then I also prepare a field which is called pi, which you can, if you want to think about it, just think about parent, like the node that will tell me how far I am from the source. So at the end, what you will see is that if some node is 4 away from the source, its parent will be some node which is 3 away. And the idea will be that if I want to get from this node to the source, I need to find, so my parent, I will get one closer, and my parent will get one closer to his parent, and so on. And then what we are going to see is that we are going to change colors of node to gray to mean that we are now working on a node, and to black when we are done with a node. We are never going to see it again. So since we are going to start working on node S, we are going to color it gray. The distance from S to itself is not surprisingly 0. And S will not have a parent because it is its own parent. It's the starting. So the first thing that I do, and here is the crux of the difference between my description and what you are going to see in this code or pseudocode. Now the serialization comes in. And how will it come in? By imposing a regime of a queue. A queue, as you know, it's a data structure of first in, first out. So we have a queue called Q, and we initialize it to be empty. And the first thing that we do is we enqueue S into Q. So now the queue has one element. And since it has one element, and the next thing that we are going to do here, after asking, is it empty? So that's the while loop of the algorithm. Is the queue empty? And at the beginning, obviously, who will be there? Only S. So we dequeue, we take the guy at the head of the queue. We enter through the tail, we take the guy from the head, which not surprisingly is S in the beginning. We put it into U. And now what we do is the following. We go over the linked list of adjacent nodes to U. And for each of them, one after the other, we pick the guy out, and then we start asking. So we do it, we go through the linked list of all the vertices adjacent on the vertex that we examine now, meaning U. So we go over all the vertices in the adjacency list of U. And as we pick them one after the other, we look at the next one and we ask, what is your color? If the color is white, then it means that we reach you for the first time. So what do? We color you gray. So if somebody else will look at you, they will know that somebody already visited you. And then we increase we set your distance to be the distance of the current U plus 1, because the fact that you discovered you means that nobody discovered you before. And we set your parent to be, parent of this new node, to be you, because you found it. And as I said, I already told you to expect that the parent the distance will be one less than the node, which is exactly what you see here. And the last thing that we do, because before we leave for now the current node that we just discovered, we enqueue it, meaning we add it to the tail of the queue. And once we finished going over the all adjacent nodes of U, we color U black. We are never going to see it again. Next thing that we do, we go to the queue. We take the guy at the head of the queue if it is not empty, and we do it the same. And somehow, the queue regime will guarantee that I, in a way, serialize the wave. So instead of advancing, so what's going on here is that while I describe the wave as going forward in parallel, what you see in this code is that we go to the next pulse of the wave, and now we start going through the wave serially. Okay, so we have here two dimensions. One, we advance to the next level or distance, and then we start going serially and execute the wave as if we take each of its points of reach out and treat it serially rather than concurrently. So this is really the connection between the parallel and the serial outlook, and what made the serial outlook work, or how did we express it? We express it by using this data structure known as a queue. Okay, but so what is the purpose of the queue? The purpose of the queue is not to actually describe breadth-first search as a native procedure. It is completely different. It is to implement breadth-first search serially. Is this point clear? So the role of the queue is not identical, and that's where I'm really upset about the way that it's presented in the book, because the book tells you there is no breadth-first, there is no BFS, no breadth-first search without a queue. And this is highly misleading, because breadth-first search exists with or without a queue. So I hope that the point is clear. Okay, now that I've described it to you, let me go and do, by way of drilling, I am going to execute this pseudocode on the example that we already started seeing before. So imagine that this is my input graph. And now, what did I do? I took S, I made it gray, right? And now, I put it in the queue. Okay, so you see the queue has just one vertex, S, and what is the distance to S? It is 0. So now I'm doing the iteration where S is the head of the queue. So what am I going to find? The first node that I'm going to find, let's say it's R. No, I apologize for that. The first node I'm going to find is W. How do I know? Because I look at the queue, right? So I find first W, I put it in the queue, and then I declare W to be 1 away, and I make it gray. The next node that I find is R, because I'm still exploring the adjacency list of S. I put it in the queue and declare the distance to it 1, and of course make it gray. So now I'm done. So I turned S to black, and I'm going to treat W because W is now the head of the queue. So let's see what I do with W. So I go to W, and I find first X, no, first T, I'm sorry, first T, then X, and each of them I mark, I tell them, I'm your parent, and I mark them as being of distance 2. And when I'm done, I turn my own color to black. So now, who is the head of the queue? The head of the queue now is going to be R. So what do? I go to R, and from R, I look back at S, and I forgot that here I also look back at S, and I don't do anything because S is already not white. So here I look back at S, I do nothing. I look at V, and V was white, so I make it gray, and I tell it your distance is 2, and I'm your parent. Okay, next node. Next node is T. So from T, I look to W, and I do nothing because W is already black. Then I look at X, and I do nothing because X is gray, it's not white. Then I look at U, and I find that U is white. So what do? I turn it to gray, I declare its distance to be 3, and I add it to the tail of the queue. Okay, next, I go to X. From X, I explore all 4 edges. I go to W, it's black, I do nothing. I go to T, it's black, I do nothing. I go to U, it's gray, I do nothing. I go to Y, and I see that it's white. So I turn it to gray and declare its distance to be 3. Okay, now you can already be prepared to anticipate what will happen from now on, because what you see, if you look at visually the graph, you see that all vertices are already non-white, right? None of them remained white. So what you can expect now is a winding down of the algorithm, because basically it has nothing more to do. The only thing that should happen is that it should figure out that it has nothing more to do, because you see it, but the algorithm really needs to go through the nodes and figure that out. So the next vertex to consider is V. So V looks at its edge to R, and since R is black, it has no more vertices, it turns itself to black, and now we are going to pop or dequeue U from the queue. So we dequeue U, and for U, we look around, everything is already settled, or none is white. So we finish, then we look at Y. Y has nothing to do, it turns it's left to black, and that's it. So do you see the direct connection between the pseudocode and what I did in this description? Is it clear? I did it faithfully. I described the runtime. So before we go and discuss correctness and complexity, let me make a point that the reason that I consider this extremely obsolete is because the reason that it described so serially is because when the von Neumann architecture came around, and you may find in some museums how the computers that were built in the late 40s, early 50s looked. They had a tiny core. So you would bring an operand, to the core or to the processor would work on it, send it back, and then ask for another thing. The core was very small, so the whole concept of parallelism, even if some people started thinking about it, was completely off limits. Okay, now let's start asking ourselves, what happened since then? So what happened since then is not only that the clock advanced by a factor of 1,000,000 from several thousand, from a clock rate of several thousand ticks per second to several billions. What we also can do is a lot of parallelism, not also first in memory and then in processors. So this very rigid mindset of let's slow down everything and serialize is really from another world. And I find it extremely absurd that when it comes to standard material, as I'm teaching you here, this is still being taught as the primary way of thinking about algorithms in 2020. I mean, you know, it sounds like going back to a cave and telling you how cavemen lived. You know, it is very obsolete. I hope that you can at least connect to the sentiment here. Okay, so that's the my comment on breadth first search and the explanation on why we cover it in this fashion. And again, as I said, what I can tell you in my defense is that that's the way it's taught everywhere. So that's the standard. Okay, now about correctness and complexity. So we are going to go quite carefully through these two concepts here, because I think that they are really cool and represent each in its own way, a way to rigorously think about these issues. So correctness. What is the basic claim? So we look here at two terms. Delta of S of V is the correct shortest distance from node S to node V in the graph when we count edges. What is D of V? D of V is the quantity computed in the algorithm. So delta is the correct thing, D is what I computed. So what am I arguing? I'm arguing that D equals delta, meaning that I computed the right thing, right? Is the theorem clear? Theorem claim. So here is a first lemma. A first lemma is if U V is an edge in E, then the distance between S and V is upper bounded by the distance between S and U plus 1, because I can reach U via V. I may have a shorter way of reaching U than via V, but I'm guaranteed to be able to do it that way. Then at the end of breadth first search, D of V cannot be less than delta of V, or it got to be larger than or equal. Why? Because D of V gives me an actual path. Remember how I can compute it. I go to my parent and from that to that parent, and inductively I can prove that if I follow the parent relationship, I'm going to reach S. So this means that the construction of the algorithm guarantees that if I tell you that the distance in D of V, even if I'm wrong and it's bigger than what it should be, it represents a true path. Okay, so these are just easy way of starting to think about it. But what we really would like to argue is this, right? That the computed distance is the correct distance. Turns out, and it's a really very nice way of articulating induction rigorously, is that the way in which we are going to prove it is, instead of having a single item inductive claim, we are going to argue the inductive claim using two items. And let me go through the two items, and then I will explain why there is a certain subtlety in the mathematical subtlety in this argument. So the inductive claim is the following. If d of v is at most I, or less than or equal I, then at the end of BFS, d of v will be the correct distance to v. And the second item is that if the correct distance is at most I, then at the end, the same claim, delta of SV will be equal to, the computed will be equal to the correct. So let me put the inductive claim in words. It is saying two things, and the integer I is playing a major role in both. It says, if you tell me that the distance that you computed is larger, is less than or equal I, then what you computed is correct. And if the correct distance is less than or equal I, then what you computed is correct. Now, why is it so subtle to argue both? Because if this is my inductive hypothesis, it will be trivial to get from it the inductive claim. So let's assume that this is correct, the inductive hypothesis for I, and let's prove the inductive claim for I plus 1. Okay, so what do I need to prove for I plus 1? I need to prove both items. But what I'm allowed is to assume both items for I, right? So telling you, if d of I is less than or equal I, then automatically I already have it in the assumption. But what if d of v is equal I plus 1? If d of v is equal I plus 1, then by the computation, and because of the lemmas here, I know that there is a node u whose computed distance is I, that gave v the label I plus 1. The distance to this guy was correct by the inductive hypothesis. Okay? And for that reason, d of v is at most I'm sorry, so this is d of v, so it's I plus 1. Okay, so let's put this aside for now. So we have another node u to whom the distance is I. Then let's make the other assumption. If delta of SU is I plus 1, because if it is less, we already have it automatically in the inductive hypothesis, then at the end, delta of SV is equal D of V. Okay. So now that I have both, I can also assume that there is a U such that the correct distance is to U is I. Okay. And now let's say, assume by contradiction that D of V should have been I or less. Clearly, I get a contradiction to 2 in the inductive hypothesis, right? Because it means that I should have computed it before. If on the other hand, the distance, the correct distance should have been less. But I only now found it, then I get a contradiction to 2. And if so in both cases, what I'm trying to say is that I get a contradiction to one of these terms, and for that reason it is correct. Should I go over it again, or is it clear? I wonder if I said it clearly enough, or should I go over it again? Please don't be shy. Okay, so what I'm trying to say here is the following. By having these two items together, what's going on by coupling them together, if I for an item which should have been I plus 1, because I get a prior item which is I get a contradiction either here or here, whether it's computed I or whether it is the correct I. So by doing both, I'm not allowing the correctness, the inductive claim to hide anywhere, because I carry both at the same time. So I'm not allowing any infringement. It's both correct and includes everything. So these are the two claims that, if you really want to translate it into different terms, is that we have here two entities, what we computed and what is correct. And this claim is actually tells me that the computed value is I, if and only if the correct value is I. That's the way to combine the the inductive claim into something which would be a single unit, but in fact, if and only if means that we have two items. So that's what it is. Okay. Questions about this this construction? Okay, so I would like to proceed now to demonstration of the complexity analysis. So the complexity analysis is going to be a demonstration of the charging method. Well, what you see here is a restatement of this pseudocode, and what you will see here is the following. We take each and every line in the pseudocode, and what we write on the left-hand side is an entity in the input graph to which we charge the operation. Now, what's going to be the big insight? The big insight is that I'm going to argue that no entity, no vertex, and no edge are going to be charged more than a constant number of operations. Which means that if I charge 3 operations to vertices and 5 to edges, what is my overall complexity? It is 3 times n plus 5 times n. In other words, it's big O of n plus m. So that's the framework. Does the framework make sense? Okay, if the framework makes sense, let's now see how we implement it. So for the initialization, what we do, oops, just a second. For the initialization, this is the initialization stage before we start the while loop. We go over all the vertices, we initialize them to white and so on. So this is clearly 4 operations that we charge to the vertex U. Then we go to the vertex S, we initialize it. Not surprisingly, we charge it to S. Now we do the NQ, so the NQ will always be charged to the vertex being NQ'd. And when a vertex is DQ'd, we again charge it to that vertex. And since this is a Q, and it's not very difficult to argue that no vertex will be discovered by this algorithm more than once, because once discovered, we change its color. So every vertex will be NQ'd and DQ'd exactly once, right? So this is where we NQ, and this is another place where we NQ. We always NQ the guy who, charge it to the guy who is NQ'd, and then when we DQ, we always charge it to the guy which is DQ'd, to the guy at the head of the queue. Again, not surprised. Now, what happens next? So when we do the while loop, here we start going, so the only operations I haven't yet accounted for are the operations where I visit one edge at a time for the vertex which is at the head of the queue. So here I look at the edge going from U to V. So I'm looking at this edge. There are really 2 possibilities. Either the vertex on the other side is found for the first time or not. Regardless, I charge this operation to the edge, because the way the algorithm proceeds is that each edge is going to be traversed only once from each of its endpoints. So I charge it to the edge. These 2 operations I charge to the edge. Everything else I charge to the vertex on the other side, because what will be the only condition where I will execute rows 14 to 17? It's only if vertex V is visited for the first time, right? And how many times is a vertex visited for the first time? Right? Think about it. You visited only once for the first time by the definition, right? And it's clear, right? So that's it. So this actually establishes, in a way, as part of the charging. I already gave you the proof for why every item is being charged no more than a constant number of operations. So is the proof that the complexity of the algorithm is linear clear to everybody? And this is for the adjacency list representation. If you think about in a matrix, when I do the adjacent here, I will go over all the rows of the matrix. So because I will not have an adjacency list, so the complexity will go up to n squared. Okay. So now this is a point that I already made, but just to be sure that it's clear, if now you tell me, okay, you found that the distance of vertex v is 55, but where is the path? The answer is that you go to vertex v, and what you do is you recursively, you ask who is your parent, and you find the path all the way to S. Okay. The next procedure we are going to study is the other thing that you could do instead of breadth-first search, which means do depth-first search. So what is the idea of depth-first search? So the beauty of the code here is that it is quite short, or I'm not sure it's much shorter, in fact, but it actually conveys the notion of breadth-first search as a recursive call. Because similar to recursion, you call something and then you keep unfolding it until you cannot go anymore. Then you come back, then you go again. When you come back, you go again, and so on. So that's really the spirit of depth-first search. So let's see what's going on here. In the beginning, we go to our graph G, and for every vertex, we color it white, and its parent is nil. But now we also have a notion of time. And as we are going to see, the time or the pulse, it's going to be pulses because it's going to be discrete time, is going to play a big role. So we initialize the time to 0. And now what we do is the following. We go to every vertex, and if its color is white, we initialize depth-first search visit, and depth-first search visit is going to be a recursive call. So far, we haven't seen recursion. We're going to see DFS visit of U. Now, this is a bit confusing. Why is it confusing? Because I'm telling you that this is another way of traversing a graph. But I'm telling you, if a vertex is white, I start a process. But this is confusing because don't I expect in the traversal of white to never have another vertex which is white? What is the whole idea of traversal? That I'm going to cover everything. And the answer is that the only way where I'm going to come back to this for loop and execute it again is if the graph is not connected. Okay, so that's the only chance where the for loop here will require actual execution, because this tells me go through all the vertices, but in fact, I will never need to execute this again if the graph is connected, because this recursive call for the first vertex I work on will reach everybody, and once I start it in a connected graph, I will never find another vertex which will be white. Okay, so I hope I didn't confuse you with this state. Let's see how the recursive call works. So I do a recursive call at node at a certain node here, let's say U. So the reason that I color it gray is because the reason that I put it there is because it is white. And as we see, upon calling recursive call to a vertex U, it's always white. So when we enter this first thing, we mark it as gray. And the next thing that we do is the following. We increase the time by 1. Remember, time is discrete. And I declare the discovery time of this node, which D of U here means discovery time, to be this time that I first entered this node. Now I start going through its edges. But it is very important that you try to catch with your eye the huge difference between this for loop right here and this for loop here. Do you agree that these two for loops are written in the same way, right? For each V adjacent? Is that clear? Still, they are going to be a word apart in their execution. The command number 5 is not going to still tell you in which ways they are going to be a word apart, because they both ask, do if color V is white. If it's not white, don't do anything. So this still doesn't reveal to you in what ways they are different. The next command also doesn't reveal it to you, because it tells you, make U the parent of V. But look at command number 7. Command number 7 throws you off to a completely different control. Why is that? So let's see what's written in command number 7. df visit of V. What was written in the analog command, which was which are really 14 to 17 here. They say color it gray. We had that. Do some distance and then NQ. So you see the big analogy is the NQ, as opposed to DFS visit V. Why is it such an enormous difference? Because what is NQ? NQ tells me, put it on your list to do. Deal with it later. What does DFS visit of V tell me? Make it now your top priority. Forget about everything. This is the next thing you need to do, because you stop here in this recursive call, and the next time that you reach this command can be a long time from now, because the recursive call can keep you busy for a very long time. Do you see why there is an enormous difference between this very innocent single line? It looks very innocent, but it's a very completely different control mechanism. Do you have any question about it? Because that's really a fundamental point. If you understand that, the rest is really detail. And that's really the difference between this more iterative description of breadth first search and the recursive definition of depth first search. Okay, so what it tells you, go advance, figure out how far you can get, then come back. And once when you come back, and assuming that you already exhausted all the vertices adjacent on U, and none of them is white anymore, and so on, then color it black. You finished. Mark the finish time as time plus 1, and return control to the one who called you. Right? This is an implicit thing that you always have in recursive calls. Okay, so now let's try and see how this looks on an example. And so let me grow this a bit. Okay. Okay, so let me try and demonstrate it on this example. Okay, so what's going on here? I start at node U, and then I do DFS of U. At this point, only U is gray. So U has, and here it is demonstrated on a graph which is directed, but it will be the same for a graph which is undirected. It doesn't, that's not the big deal, at least for the definition of depth first search. So let's see what's going on here. I start at U, I mark it gray, and I mark its discovery time as 1. What happens next? I look at its outgoing edges of U on adjacent U in order, and it turns out that the edge to V appears before the edge to X. So I look at V. V is white. So what do? I shift control to V, make it gray, make its discovery time 2. What happens next? Next, V starts looking at its adjacent edges. The first that V looks at is the one going to Y. So it transfers control to Y because Y is white, make it gray. Now we do DFS for Y. And we increment its discovery time. We set its discovery time to 3 because it's it's the prior 1 plus 1. Now we are at Y. From Y, we look at its outgoing edges. We have 1 going to 4. 4 was white. We transfer control to 4. Now 4 becomes gray. 4 becomes gray. It gets a discovery time of 4. And the control now is at X. So for X, what we do, we look at this edge leading to Y. And what do we do with it? The answer is we do nothing. Why? Because V is already, the X to V, V is already not white. So what do? We go from here. We conclude that we have no more edges. We mark the finish time of X as 5, and we backtrack to its calling procedure, which is Y, came from Y. At Y, we have nothing to do. So we mark the finish time as 6. We mark it as black. We turn the current to black. Here was the first time that we had the black. And we backtrack to 2. At 2, we have nowhere else to go. So we mark the finish time as 7. And we turn to black. And we go back to U. At U, what we do, we now look at the other edge that we had, and it goes to X. But X is already not white, so we do nothing, and now we turn the finish time to 8. Now, there are 2 terms that I skipped on before that I wanted to bring to your attention. And we are going to discuss it at length at some point later. This edge from 4 to 2 is considered a back edge. Why? Because 2 is an ancestor of B, because when I went from X to V, the way that recursive calls are implemented is by way of a stack. And V was still in the stack. Now, on the other hand, for U, the edge to X is considered a forward edge because I found it after I backtracked to U, and when I was at X, U was in the stack. So because of that, you have a parent, an ancestor-descendant relationship between U and X. So this makes it a forward edge. Okay, from now on, it should be clear what's going on. So now we backtrack to the calling routine. So remind you, the calling routine is this. Observe that what I'm demonstrating next is a situation where we started here with a vertex. We did these recursive calls. Now we backtracked because we cannot continue using recursive calls. So we backtrack to this calling routine, and we start going over the vertices. So we may next, after we backtracked here, we may look at V, we may look at X, at Y, all of them are black. The next vertex that we find, which we have not yet marked, which is still white, is W. So suppose we look at W here, and from W we start exploring. First thing that we explore is going here to Y, but Y is already visited, it's already not white. So we call this edge from W to Y, we call it a cross edge because there is no ancestor-descendant relationship between W and Y. So Y is already out of the stack, and W is in. So, but it's not a forward edge because even when Y was in, W was still not in. So it's not a back edge and it's not a forward edge. So this is called a cross edge. Next thing that we do is that we advance from W to Z. We mark it as gray. And now at Z, we find that you have this self loop, which we mark as a back edge. In any case, we mark the finish time as 11. We go back to here, mark it as 12, and we are done. So this was the drilling of this code as written there. Do you have any questions about in what way what I demonstrated on depth first search constituted a drilling of the pseudocode here? Okay, so even now that our time is up, I'm just going to tell you that next time I'm going to discuss the property of the edges of the graph relative to depth first search, and it turns out that there is a very interesting distinction between directed graphs and undirected graphs. And of course, we are going to discuss the complexity, but really fun part is discussing applications of depth first search. So we are going to resume more or less in this slide. This will be the first new slide that we are going to discuss Wednesday. One last announcement. I posted an announcement on the ERMS website that Monday, a week from now, I will allocate time to review of questions ahead of the midterm, which will be a week from Wednesday. We're on the 28th. But the way I do review sessions is that I do not do anything initiated by me, simply because it's too broad and I'm not sure I know what to do on my own. But I will be glad to respond to any question coming from students. The only condition I have is that I want you to send me by email any question you may have that you want me to review 24 hours before the class on Monday, a week from now. So I promise that you will get an answer for any question you ask up to 24 hours before, which means about noon on Sunday, the 27th. Are there any questions about that? Okay, so in this case, we finished. So see you Wednesday.